time for you.
Yes.
Okay, maybe 10 seconds and we'll start.
Okay, so our first speaker is Riemann Nagloo. He will talk about generic Schwarz triangle equation.
Thank you. Thanks for the organizers for the invitation to speak. So this is joint work with James Freitag. So basically, this is an application of some of the works that you might have seen me talk about the Fuchsian groups. And so we apply them to the generic Schwarz triangle equation. So let us start. So the starting point for this talk is the Riemann hypothesis, mapping theorem. And so, which state that if you have a non-empty, so if you have a non-empty simply connected open subset of C, so proper, so not all of C, then there exists a biholomorphic map from D to H, where HD is the complex upper half plane. So this is a weak form of the uniformization theorem. And so this is an existence theorem that says that any non-empty simply connected open subset is biholomorphic to the upper half plane. And so there's a more refined version of that that says that if you have if D is bounded by, so nicely bounded by continuous, so let's say simply connected contours, simply closed contour, then you can also extend that biholomorphic map on the boundaries. So it's a biholomorphic map. And so, but this is just an existence. It does not really discriminate between different kinds of D. So in this talk, we're interested with so-called circular triangle. So these are triangles that are formed by a circular arc. And so they come in with three parameters, alpha, beta, gamma, which basically describe the angles of the triangle. So here's a circular triangle, and so the angle here is pi over alpha, pi over beta, and pi over gamma. So let's call these vertices V1, V2, V3. So this will be the kind of D that we are concerned in this talk. And so it was, yeah.
Could you clarify, so do you claim that alpha, beta, and gamma are uniquely defined triangle up to isometry?
Yeah. So and indeed, so in this case they are real numbers. Mm-hmm. So they are real. So you need all of them are for some technical reason you can take them to be zero. So the real numbers satisfying that. So then it defines a triangle up to isometry. Exactly. And so it was Schwarz. I call it theorem. That sort of look at this particular case, and his result is that Now the unique, so I'm going to explain in a second, map as above, so as given in the Riemann mapping theorem. So I'm going to call it J gamma, taking the triangle to H. So here again, I'm using the stronger version of the Riemann mapping theorem, where I can talk about mapping the boundaries of the various objects. So this map, it's unique once you send 3 point.
What do you mean H bar?
So yeah, thank you. A path of planes, so it's boundary. Thank you. So sending V1, V2, V3 to infinity, 0, 1. So the unique map sending, so once unicity is obtained, once you specify where 3 points are sent, then this unique map satisfies a Schwarzian equation. So S d by dt of y is equals 0. Okay, so these unique biholomorphic map are called the Schwarz triangle function, and so that's what we call the Schwarz triangle differential equation. Okay, and so I won't say much, but you must have seen the Schwarzian derivative quite a bit now, and so this is the rational function is simply given here, and it matches because the singularities of this equation are precisely the point where the vertices are mapped to. So there's some significance. So that's sort of this is just an existence, and this tells you the actual function, what the explicit differential equation will satisfy. Okay, and so.
Ronnie, and
Yeah.
the R looks asymmetric with respect to alpha, beta, and gamma because one of them goes to infinity, right?
Yeah,
And
absolutely,
okay.
absolutely. So this is 0, 1, and then sort of a
Okay.
stick.
Thank you.
Thank you. All right. So now these are the equations we want to study, and sort of the relation to the Riemann mapping theorem is the importance of these functions. And so I'll call these equations, I'll denote it by Schwarzian equation. And so what we want to know, we want to look at the generic parameters. And so by generic, so I mean that the alpha, beta, gamma are algebraically independent over Q. Okay, and also one thing we look at a little bit more more general equation if you want. As I said, if you look at triangles, the alpha, beta, gamma are supposed to be real numbers, but when we look at the Schwarzian equation, we allow for complex parameters. So we look at more general parameters, but it includes the triangles.
What do you mean SW? What's the S?
Right, so that's what I call, so I won't write the equation all the time, so I'll write SW.
Oh, sorry.
Thank you. All right, and so let me sort of go through what the statements of our theorem are. So throughout, or if you want as needed, so U will be,
So this again. So this becomes a uniformly definable family, a collection of
exactly.
ODEs.
Yeah, exactly. It's a uniform
ODEs of
defined over the
order 2.
order 3, right?
Order what?
Order 3. So you have one more.
Sorry.
So it's an order 3 uniformly defined, and these are the ones we're interested in. And so a universal differentially closed field of characteristic 0. So C, I'll take C to be its constant. And as and when needed, C will be the field generated by the parameters of the equation. And finally, I'll denote by X, alpha, beta, gamma, the solutions of the Schwarzian equation in my differential equal set, the definable set we're interested in. And so the two results that I want to talk about today, and hopefully I'll be able to go through the entire arguments. So theorem 1 is that the generic solution set for the equation is strongly minimal. Again, so for those who've seen me talk, I hope it's getting more and more familiar, but let me remind what it is. So that is for any k differential field extension of my base field C here, let's say, and any solution so if I look at any solution, I have the transcendence degree over K of a differential field generated by the solution is 0 or 3. Okay, so there's no order 1 or 2 differential subvariety defining over any differential field extension.
That's not quite the same as one.
Well, so it's in this special case where you can write. Well, yeah. So in the case of these equations, so you would take the advantage that you can write them as y prime prime prime.
What?
So this I can rewrite it as y prime 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 equals.
Yeah, there's unique.
Yes.
There's a unique type of
exactly. And so there's a unique
of
type,
the generic type.
and I can define strong linearity in this way. But Tom is absolutely right. This is not enough usually to define what strong linearity is, and maybe this looks like a C. And so that's the first result. And so if you know the work that James I and Guy Casal did, that might not be surprising. So you might already start thinking of how to prove such a thing. We needed to do to look out and try to understand a little bit more the structures as what I call theorem 2 is that, again, the generic equation solution set is what's called strictly disintegrated. As short to say that, again, for any differential field extension K of my base field C and any now distinct solution,
Ronnie,
yeah.
when you say the transcendent degree is 0 or 3, do you mean for all k is 0 and for all k is 3?
No,
Or
so for
sometimes
all
it's
k-
sometimes 3.
Sometimes it's 0, sometimes it's 3. No,
Depending on K.
so depending on K and the solution you take.
Depending on
Yeah.
K. Only both.
Right.
And the Y.
And the Y,
And
the
the Y.
solution, yeah. So this time, if I take n distinct solution, and I look at the transcendence degree over K of the differential field generated by the n distinct solution, you get that it's 3n. And so here I must say distinct generic.
You just mean non-algebraic.
Say that again?
You just mean not algebraic over.
Yeah, not algebraic
Not
over C.
over K.
Yeah, so let's say not algebraic. Not in K actually. So not in the algebraic closure of the base field you take. So that's.
Well, you could just say equals the sum of transcendence degrees of individual.
Yes, that's another way to put it. That's shorter for me to just do it this way. Another question?
This is definition of strict disintegrated.
It's.
What does it mean? What is definite? What's strict?
So we usually.
I forgot what it means.
So there's no algebraic dependencies at all between generic solution.
Isn't it just the? Didn't it mean that the whole set is indissoluble?
Sure.
That's what it means.
Same.
Yeah.
It's not exactly true. No, but there are algebraic solutions. There are algebraic solutions. So there could be algebraic solutions.
So you would go over.
How many algebraic solutions?
You want to look over C alg.
It's algebraic categorical.
Yes, it's Aleph 0 categorical. But if you want to, I think it boils down to looking at C alg, and there's no solution in C alg. Right, because any dependency over K will be witnessed over C alg, and there.
So you're saying really,
Yeah.
the solution set is indissoluble.
Yes.
For the term.
Yeah.
Indissoluble
Yeah.
solution.
Yeah.
That's it.
All right. Okay, so let me now say a few words to why if you.
I mean, you mean accepting the possibility that some of the things are in K
No, but
or
you-
K.
I mean,
No, they're not.
forget about just work over C.
Yeah, because
Oh,
we can.
sure.
Yeah, because
Oh,
we can.
It's simply
I-
that Solomon set is
Yeah.
now indissoluble set.
Yeah.
And that tells you everything.
Yeah.
Yes.
Yeah.
You're right. You're right.
All right. So now I'm gonna try to explain first why I say this one is. If you know a little bit the work on that Alan and I had on the Penderby equation, it might not be too difficult to get. And why for this one you need to go a little bit deeper into the work that we had with James Guy and myself. So for that we look at so-called Fuchsian triangle groups. So here again, so I still have a setting where I have a triangle with the parameters alpha, beta, gamma, and J triangle will mean the unique map sending the vertices to infinity 0, 1. So what's well known is that the inverse of this function, the inverse function is a quotient of two linearly independent solutions of the hypergeometric equation. So now it depends. So how many wants to see? It depends. If you want to see the hypergeometric equation, I write it down with the relevant parameters. If you know what they are and don't want to see them, won't write them down. So anyone would like to see the hypergeometric equation?
How about yes?
Yes. All right. So in this case, so. There's a y. And so there's, let me finish writing it and make a few comments. So first comment so we started with, remember, the derivation was d by dt. And the y was the variable for the, in the Schwarzian equation, right? So here we have that the y is, because we're talking about the inverse function, and so we're looking at the derivation d by dy, so there's a sort of parallel to look back, because we're looking at the inverse function. And so what are these a, b's? So quickly, so a is simply, I don't know if that's not of value, but I'm just going to give one example of, so the a, b, c's are related by the parameter 1 over alpha, okay, and 1 over beta. So there are more expressions. I don't think it had any value to write them down. And it's not too proof of that. It's not too difficult, modulo understanding that the Schwarzian equation behaves very well when it comes to a function and its inverse. So then there's a way using the Schwarzian where a function and its inverse has pretty much the same ODE that they satisfy. Okay? And so why is that important? So let me bring in a definition. So the image under of the monodromy group. So if we look at the monodromy group of the linear equation, and we look at the image of this monodromy group, that's what we call the projective monodromy group of the equation. And here's what the idea is. If I give you the monodromy group, it acts by multiplicative action on vectors of solution of the hypergeometric equation. So if we're taking quotient, then this corresponds to an action of a subgroup of PSL to C, let's say, by linear fractional transformation. Okay? So if two linearly independent solutions, you act by multiplication. When you take a quotient, you act by linear fractional transformation. And so linear fractional transformation is sort of very much intertwined with the Schwarzian and with this J triangle. And so what Schwarz did, so again, so assume now that the triangle, the parameters in the triangle, I call them K, L, M, with, so K, L, M, so they are in, so now they are natural numbers bigger than, let's say, 1. I can take them infinity, so the quotient can be 0, right, so an angle of 0, such that this funny condition. So now if I take the parameters defining my triangle in such a fashion. This is we call the triangle hyperbolic. So these are what we call hyperbolic triangle. And in the case of hyperbolic triangle, so something much stronger can be proven, is that the projective monodromic group is a Fuchsian group. Of first kind and genus 0. So Fuchsian group, that's a discrete subgroup of PSL to R. And in particular, that's a group that Zariski dense in PSL to C. So 2J gamma is now globally defined single valued function. From H, let's say, to C. So you can't always analytically continue those J triangle in general, but in the case where your triangle is hyperbolic, you can extend that as a globally defined single value function. And the third, sort of most important, is J gamma is automorphic.
You mean, what? You mean the inverse or something?
No.
What, sorry?
Yeah, I'm confused with that too. Goes from H to C.
Yeah, oh, sorry. So there's one condition you're looking at triangles now properly in H bar. So before you could take triangle everywhere in C. So now for it to be hyperbolic, you also require that the triangle is in the upper half plane. And so is that okay? So at first we didn't specify where the triangle should be in.
What happens if one of the angles
Extends
is
to
infinite?
Is
Infinite.
So that's fine. So somehow you'll have to add the cusps and things. So we haven't done that here yet. So I'm just giving a very general.
You mean it extends to a. What do you mean? You mean
Extends to.
It extends to a. See, delta is in H bar or in H?
So delta was in. Yeah. So if you want, yes. Thank you.
It extends to a polymorphic
Yeah. So
function on H bar.
yeah, H bar. Right. Thank you.
Sorry?
Which is automorphic for.
Oh yeah, and then it's an automorphic uniformizer. Yeah. Thank you, and for gamma star. Sorry if I'm going too low. So for the monodromy group. And so for those who don't know, who've never seen automorphic uniformizers, simply mean that so the quotient. If I look at the quotient of gamma star by H, that's going to be, in the case of these Fuchsian group, that's going to be an open Riemann surface. And so if you take the compactification, that's going to be sort of compact Riemann surface of genus 0. And so let's call it X triangle, or maybe I don't have C triangle. It's a C triangle so it's going to be a curve, projective curve. And what that means, and what the uniformizer means, it means that the function field of that curve is, you can think of it as being generated by those J triangle. Okay, and so let's put an example. So that might have some.
Ron,
Yeah.
so some people noticed, but I think you should switch the place of the H in the gamma.
No.
Well, maybe you don't want to.
Yeah, no, I don't. I mean, that's how they usually write the.
Okay, you
So
really.
you know, you're acting.
Why do they write it like that?
Say that again. Oh yeah, so H. Yeah, you're right. So sorry. That's what I meant. You're right. The action on H. Thank you, Jim. Yeah. All right. So the most famous example is when the parameters are 2, 3, infinity, and that corresponds to PSL to Z. And so the well-known picture of a triangle is of something like that, I guess. So this is pi by 2, pi by 3, and infinity means the point at infinity. And then J, in the case of, this is 1 over 1/728 of the J function, 12 cube of a J function. Okay, so it's not, the uniformizers here are not it doesn't give the J function, but it's related to the J function. Okay, so what we see here is that we have a quite large family. So whenever you have natural numbers with infinity satisfying this relation, you get a group. Fuchsian group, you get a nice uniformizer. And what we did in our earlier work with Jim and Guy Casal, so that's, let's say, 2018 for now. Is that if the triangle is hyperbolic, so if you do have all these conditions on the parameters and on the triangle, then x, k, l, m, so the solution set of the corresponding Schwarz equation is strongly metal. Okay.
And more.
And more. So now I'm going to just focus on strong liminality and explain for those who never seen me or Anan or even maybe Jim talk about how we deal with a generic Penderwey equation. So that's going to be in a similar situation. So I'm going to explain how to get strong liminality of the alpha, beta, gamma from that result. And then I'm going to talk about the other result. So proof of theorem 1. So here, x alpha beta, so we're proving for generic strong limit 1. So that's what we do. Okay, so and as I said, this boils down to a sort of decent argument that we look at when we first looked at the generic Penderwey equation. So I'm going to write it as a fact about complex numbers or generic constant. So let phi x1 xn be a formula in the language of differential ring. Assume alpha 1 all the way to alpha n are constants that are algebraically independent. over Q, such that when you replace, when you evaluate, if you want, at those constant parameters, you have at its true. So if you have a formula in the language of differential field without parameters, that's true of n algebraically independent constant, then it must be the case that for all but finitely many constant in C, you must have that So that statement about the constant, if you want, will be true for all but finitely many constant in C. Okay, and so this is sort of the key descent argument. So you can start with a generic constant, and you'll be able to move that parameter in quite a large set of parameters. Okay, and so let me talk about how the idea of the proof goes. So alpha, beta, gamma are algebraic independent. So for contradiction, I assume that it's not strongly minimal. And so by definition, that means that over some, let's say, k, some differential field extension of C, I must find order 1 or 2 differential subvariety. Let's assume that it's given by a differential polynomial. That defines a subvariety of, I'm leaving, of course, details. You can write all of this formally. And so what's going to be my theta, alpha, beta, gamma? It's simply going to be the sentence that says there are parameters different than, you can say different than alpha, beta, gamma, such that together with alpha, beta, gamma, so you see the formula talks about alpha, beta, gamma, we can define a differential polynomial of order 1 or 2. So for this, you're going to have to perhaps quantify over the non-constant parameters, saying that there exist parameters that doesn't make the coefficient vanish, defining subvariety of X alpha beta gamma. Okay, so there's a way to write that formally using the language of differential ring. And so then we use this descent argument 3 times. We move alpha in the set of natural numbers, let's say big enough that it ensures that I satisfy the required. So then using fact.
Isn't the collection of KLM such that this thing is hyperbolic, like Zariski dense?
Yeah.
So it's finished.
Yeah, so that's what I'm
And theta is equivalent to a form in algebraic closed fields.
absolutely,
Okay.
absolutely. So, but I'm explaining to those
Okay.
who might not see. So I'm gonna sort of use fact 3 times to find n1, n2, n3, such that 1 over n1 plus 1 over n2 1 over n3 is less than 1. Right? So, and now what this new sentence, or what this would give, is that there must be a definable subset of x alpha, xn1, xn2, and this contradicts our original analysis that, so let me maybe write it down. So this now it means that x n1 and 2 and 3 is not strongly minimal. But that's our earlier result, that for all parameters that looks like that, you get strongly minimality. So this really is, in a lot of ways, following ideas that come up when we were working with Pender's equations. So if you have the kind of the kind of thing you want not to happen, we wanted to prove strong linearity, but strong linearity happens to occur in a large enough, so Zariski dense subset, then you can prove strong linearity of the generic fibers. So this is sort of, as I said, not if you've worked with Pender's, it's not too surprising, but the real challenge, or the real thing we needed to do, is to figure out how to now talk about algebraic relation. So So now we have strongly minimal. So we have strongly minimality. So what we want to prove is, what if I take n solution? How do I show that there are no algebraic solution at all between n solution? So this is a bit trickier. But again, in the previous work with so Casal, Freitag, myself, again, we show something quite strong. So what we show is the following. Consider a general Schwarz equation. So this is an equation, again, d by dt, y plus all right, so the difference with what is on the board now and what was before is that here, that's in C y, and it's not necessarily this guy. So it's any rational function over the complex number, right? So we call that a general Schwarz equation. So what we show is the following. So
Do you require it to be non-zero or non?
yes, so non-zero. What about constant? I think even for no. So we far as I can remember the proof. Yeah, we need that it's a rational function, so not a constant. Thank you. So what we show is a very strong sort of form of binary condition is if y1, yn is our solution, our distinct generic solution, so not in gauge of that's a K distinct K generic, where again K is any subfield of my base field K. So if you have any distinct solution such that
What is C?
C is again, so C from the very beginning, sorry, is the field generated by, thank you. So any constant field. Let's take it to be a complex number. That's fine. Or any finitely generated constant field over Q, such that y1 prime, y1 prime, and so all the way to yn prime. So if you take n distinct solutions such that you can see an algebraic relation between so the transcendence degree is not 3n, then
Over K.
over k, yeah. There, so over k, yeah. There is a p in cxy and I less than j such that so if you heard about geometric triviality, this is a bit stronger than geometric triviality. It's saying if you have any dependency between solutions and the derivation, then there is an actual polynomial, not differential polynomial, which vanish on two distinct solutions. And so what we have to do then is we have to simply try to show for the generic that there can't be any such polynomial. Okay? Yeah, that's the point. So no derivatives. All right. So it seems like time-wise, I'm gonna have to truncate things here and there. So so that's the aim. So aim is to study possible P in CXY for generic triangles, right? And so remember, our strategy is clear. What we have to do is to go back to the Fuchsian triangle group case. So what happened in the Fuchsian group case? So this is what we need to do, and our objective should be clear. We should find a large Zariski dense, maybe set of triples of natural numbers for which there are no polynomials. And then we can do the same game of the descent argument. So I'm just gonna, because of time, I'm just gonna explain how non-arithmeticity come into play. So So quickly, so by the commensurator of gamma triangle, so for a triangle group, I mean all the G's in PSL2R such that so gamma triangle is commensurable with G gamma triangle G inverse. Right, so where G1 is commensurable to G2 if and only if G1 intersects G2 has finite index in G1 and G2. Okay, so if I give you a triangle, those are the Fuchsian triangles, those where this is an hyperbolic triangle, then there's the idea of a commensurator. And what does that do? So what it does is simply for any G in the commensurator, what you have is that the intersection, so this is the intersection, so let's call it gamma G, which is the intersection of, so here I'm going to take gamma to be gamma triangle. So the intersection of gamma with a conjugate is itself a Fuchsian triangle group. So what this finite index property gives you is it sort of preserves the property of being a Fuchsian triangle group. And so then what you have is it's not hard to check that so J triangle and J triangle where we translate by G inverse are uniformizers of this group. So, and the idea is that J triangle T was the uniformizer for gamma. J triangle where you have the action by G inverse is a uniformizer for this group. So these will be the uniformizers for this new Fuchsian group. And the idea here is a theorem of Poincaré is that in that situation, there must be, if there are two uniformizers for a triangle group, they must be related by a polynomial relation. So, so there exists such that and these are called gamma special polynomials. So the most well-known example is the modular polynomial. And so what we show in our previous work with Casal, again, in 2019, is that all occurrences of polynomials for hyperbolic triangle so where we have KLM comes from one of these polynomials. And so I don't have enough time. So what the end of the story is So I'll do 1 more minute. Is that okay? 1 or 2? And so the end of the story is the following. So all we need to aim is to figure out when is so gamma triangle. So now let me specifically say that it's not for the hyperbolic one, but for the any triangle. So we want to see when. Oh no, sorry. My apologies. So when KLM, of course, when for this guy are they equal to the commensurator of, right? And the idea is when you equal your commensurator, there are no G to choose to build those polynomials. And this is what's called being a maximal triangle group. And I'm just going to write down the large set of solution where this happened. It involves looking around and putting all of these things together. Is so a triangle. So this is called maximal. So a hyperbolic triangle ALM is maximal if and only if so KLM is of the form so all right. And so if you are outside this set, you equal your commensurators. There are no gamma special polynomials. And from this, we can use our descent argument to avoid.
You're saying this, isn't it? It's not maximal, so that's
Yeah,
why.
not max.
No, it is maximal. So
No. I thought.
it's not of the form. Thank you. Not of the form. Thank you. That's very important. Not. Thank you, Tom. Not of the form, one of these forms. And so in our proof, all we have to do is do the descent argument and make sure we avoid these, and there are plenty of room to maneuver. And that's going to be the end of my talk.
Questions? Comments?
Yeah.
So this kind of descent argument works for the generic,
Yeah.
but if you had algebraic relations amongst the alpha, beta, and gamma, it's not going to work. I mean, because you just don't have enough
Yeah.
points on
Yeah.
most varieties. So do you have ideas about
So
like a more direct way to analyze these equations?
for strong minimality, definitely. So for strong minimality, what we also show in the work with Casal, Jim, and myself is we relate showing strong minimality to the Kovacic algorithm. So we plan to do that in that paper as well, to sort of look at the rational functions and sort of dig out this result to see where exactly the parameters you get strong minimality. So that we can do. But then for trying to analyze possible algebraic relation, that might be a little bit more difficult. So it involves looking for these special polynomials, but outside the context of triangle groups. It's not clear how you could define it.
Yeah, so I mean, if you're dealing with the Schwarz equations where the rational function is not
Yeah.
some type, then
Yeah.
there's no
There's no
connection
no.
to group theory that you can.
No, it's, I mean, it's maybe there are. So maybe we'll explore. But we haven't seen OA yet.
And does this approach work for covering maps associated to higher genus groups? Collectible dynamics?
So this is another thing so you see the rational function, having a rational function is intimately linked that it's genus 0. And if you're not genus 0, it's not too bad. Instead of a rational function in just y, using this theorem of Poincaré, you can show that there's going to be a sort of a rational function in 2 variables that's involved. And I think something might go through. So we're planning to look at that in the summer. Something might still go through, so where you could relate the monodromy group of the Fuchsian, of these equations, or the linear equations, and try to show some linearity. So yeah, we are hoping we'll be able to do that.
More questions? Okay, thank you.